couple of definitions here. We've got the molecular formula. That one's important. It represents the actual number of atoms in the compound. So something like glucose, right here, C6H12O6, that's a familiar compound from biology, has 6 carbons, 12 hydrogens, 6 oxygens in it. Now, we use mathematical calculations and something called the empirical formula in order to figure out molecular formulas. The empirical formula is the simplest ratio of the subscripts. So it's like the most reduced form of the compound that you can possibly have. But the empirical formula is helpful because, like I said, you can do some calculations with the moles and figure out the molecular formula. So here, if I'm looking at glucose, just like before C6H12O6, as you can see, they all have a factor of 6 in there. So you could reduce it, divide everything by 6, and you end up with CH2O, okay, as the empirical formula for glucose. So you would use the factor, that common factor, and reduce it to its lowest ratio. But I do want to point out to you here, this one right here, C4H8, what is the common factor there? Yes, the largest common factor would be a 4, so we would divide by 4, and we would end up getting CH2. Right here, tetraphosphorus deoxide here, that one is only a 2, so yes, we would reduce it by 2 to get P2O5. However, what if we have something like N2O3? Is that reducible?
No.
So guess what? In this particular case, when it's not reducible, the empirical formula is the same as the molecular formula, and you can have that situation. Same thing here, CH2O, which is formaldehyde, organic compound. It is not reducible, so it would be also the empirical formula as well. Now, using information to figure out the empirical and molecular formulas. Usually what's going to happen in the problem is they're going to give you percents. They take the unknown substance, they stick it in a machine, and it calculates the mass of each particular element in there by percentage. So, for this particular case, a compound consists of 72.2 magnesium and 27.8 nitrogen by mass, okay? You're going to follow these 4 steps in order to figure out the empirical formula. So, the first step is percent to mass. Kind of is a little rhyme, help you remember the steps. Percent to mass, mass to mole, divide by small, multiply till whole. And when I'm referring to divide by small, we're talking about the smallest moles. And then you multiply until whole if you get something that isn't a whole number. So the first thing you would do, very easy step, is take the percentages and just write them in and put a G by it. Change it to grams. 27.8 grams. That's the first step. Take off the percentage sign and put a G. Really not that hard. Then the second step is changing the mass to moles. That's very easy. Okay? We would do a quick little T-chart, 72.2 grams of magnesium. We know the molar mass is 24.31 from the periodic table. 24.31 grams equals 1 mole magnesium. And then we get the mole amount. So what is the mole amount here? Realize too, 72.2 has 3 digits in it, so you would want to keep your moles to have 3 digits as well. So we would make this 2.97. Remember, taking the 72.2, dividing it by the 24.31. We also want to do the same to our nitrogen. We have 27.8 grams of nitrogen divided by its molar mass, which is 14.01 grams. That equals 1 mole. And what do we get for the moles of the nitrogen?
Wait. That's
we get 1.98 moles. Very good. Now, so we've done percent to mass, change the percentage to a gram. Second step, change it to moles, dividing it by its molar mass off the periodic table. Then, now we have the moles. Out of our 2 mole values, we have 2.97, 1.98. Which one's smaller in value? The nitrogen value is smaller. So we're going to divide everybody by the nitrogen's value. So that's going to be 1. We're going to divide this one also by the nitrogen value. And what is that going to come out to be? 1.5. Okay, so in this case, we didn't get all whole numbers here. When we divided by the smallest, we did not get all whole numbers. So then we have to do the last step, which is multiply till whole. And what could I multiply everything by to get whole numbers?
2.
Easily multiply everything by 2, so this ends up being 3, and this ends up being 2. So my formula then is Mg3 and 2. So those numbers become the subscripts of the formula.
Would N2 and G3 also be fine? Does the order matter?
Yes, it does matter because in this case you would always write the metal first, then the non-metal.
Okay.
So in this case, usually you just follow they'll give you the percentages in order of how they are in the compound, typically. Okay, so this is using the different rules to do the empirical formula. Now, there's extra steps to get to the molecular formula. So we're going to take a look at an example like that. Here, I set up most of the chart for you so we can get on. All right, so here in this particular problem, finding the empirical formula, some of the steps have been done for you. Okay? So they gave you 3 elements, carbon, hydrogen, and oxygen in this particular one. So this is organic. They gave you the percentages, 68.54%, 8.63, 22.83. They changed them to the grams for you, okay, like so, and set up the little T-charts for you very easily here. And you can set your problems up like a little table and keep it in order that way by the elements. It's very helpful. One thing else, though, that I want to point out that you'll find in the molecular formula problems, they always give you the molar mass of the molecular formula. So they add that extra piece of information in for you. So they add in that molar mass, extra little bit there, for the molecular formula. But in order to find the molecular formula, we first have to get the empirical formula. So let's all calculate the moles real quick. Get those values. Write them down. 68.54 divided by 12.01, which is the molar mass of carbon. Now, the percentage had 4 digits in it, so I'm going to keep 4 digits. Uh, 8.63 divided by 1.01, which is the molar mass of hydrogen. That one only had 3 digits, so I'm only going to keep 3 digits in the moles. If I wrote that wrong, it's 5.4. Transpose my numbers. There we go, better. 22.83 divided by 16 for oxygen, and you keep 4 digits here, 1.427. So we did percent to mass, mass to moles. Now we look at our moles and divide by the smallest. Smallest being our 1.427. That's going to give me a 1 here. What is our value there for the moles? 5.98. Okay, so we're going to make that a 6 because it's very, very close to 6. Like so. It's virtually 6, so that's what we're going to do. And then the last one, the 5.707, divide that one. So this one ends up being 3.99, so we're going to make that a 4. Now all of our particular ones came out to being whole numbers, virtually whole numbers, so we get to stop here and we don't have to do the last step. We don't have to multiply till whole because they're already whole numbers. So this one we don't have to do this time. Now we can write out our empirical formula here. We have C4H6O. So we got to the empirical formula, that's great. Doing the same steps that we did before, percent to mass, mass to mole, divide by small, multiply till whole. Yes? It will be very close. It'll be like 9.9 or 9.8. If it ends up being a 0.5 or like a 0.49, you know that's going to be a multiply by 2. If you end up with a 0.33, say you end up with something like, you got like 2.33 as one of yours, or 2.34, or even something like 3.67, what would you multiply by to get those to be whole numbers? These ones would all get multiplied by 3 if that ended up being how it looked. But the ones that are going to be just, you can round up to the whole number, are going to be very close, like 9.9, 9.8, 9.7, very, very close. These guys you would multiply by 3. 0.5s, you would always multiply by 2 to get the whole number. These are the main combinations that you'll see. You won't see anything that's really strange in terms. A third, 2/3, or a half, basically, are the only decimals you're going to see here. Okay, that was a very good question. Now, finding the molecular formula, we have to do one step before we can get there. We have to find the empirical formula's mass, the molar mass of the empirical formula. So, all I have to do then is grab my periodic table and look at the molar masses, although it's kind of up here on the chart for you already. So carbon, there are 4 of them, 12.01, plus our hydrogen, there's 6 of them, 1.01, and our oxygen, there's only 1, so we'll just add in that 16. So our empirical formula's mass becomes how much? What do we get for that empirical formula's mass? 70.10 grams. So once we get that amount, we refer back to our problem. How much did it say our molar mass was of our molecular formula? 140. I need that value now. I'm going to take my molecular formula mass of 140. I'm going to divide it by the empirical formula mass of 70.1. And what do I get pretty much there? 140 divided by 70 is pretty much 2. I call this the multiplying factor. So then you would take your molecular formula, your empirical formula, the reduced one, take your empirical formula and you multiply all the subscripts by the multiplying factor. So we would do 2 times 4, so that would be C8. We would do 2 times the 6, and that ends up being H12. And then we do 2 times the 1, and that's O2. So that will be my molecular formula for this particular problem. What I would like you to try is complete 1 through 6 here, and then start on number 1. Set up your table, and then we'll go over those answers in a minute. So if you want to take a look and check your answers for those real quick, you can go ahead and do so. 2 of them remain the same because they're not reducible, 1 and 5. The other ones, just look for the common factor and reduce by. I'm going to start setting up number 1 down here. Okay, so as you can see, I go straight to grams. I see the percentage, I take that off, I put the G there, set up my little T-charts to change them all to moles, percent to mass, mass to moles. And since like nitrogen, carbon, and oxygen all have 4 digits in them, I'm going to keep 4 digits in the mole. Hydrogen, I will only carry out 3 digits. So let's go ahead and do that. Okay, so I got the moles of each now. I look for the smallest, happens to be carbon. So I'm going to divide everybody by carbon's number. And oxygen, as you can see, is so very close that that's also going to result in a 1. So this one's pretty much 2. And this one ends up being 3.9H, which is virtually 4. So we would write out our empirical formula, N2H4CO. And then we would move on. I want to show you one other little variation of these types of problems, because sometimes they don't make you do the entire empirical formula. Sometimes they allow you to skip that. Like for instance here in number 4 on the next page, if you see a problem like this one's actually easier and less time consuming because they provide you the empirical formula. They tell you the empirical formula, so you don't have to find that. They still tell you the molar mass of the molecular formula. So basically you're just doing the last steps of example 2. All I have to do is find my empirical formula's mass, which is easy. That's 12.01 for carbon, 1.01 for hydrogen, so that's 13.02. That's my empirical formula's mass. Now all I have to do is take my molecular formula's mass, 78.11, divide by 13.02, and I get my multiplying factor. In this case, my multiplying factor ends up being 6. And so then, what is 6 times 1? 6 times 1. Our molecular formula happens to be C6H6, which is benzene. One of those fun organic compounds. So these problems, they skip all the percentage stuff at the beginning. You just get to do the ending part where you do the empirical formula mass, and then you divide and get your multiplying factor, and then you multiply the subscripts. So some of them are like that. Some of them, they give you the percentages, and you got to do all the steps. So keep that in mind.